Okay, guys, so let's start.
Hello everyone. My name is Rafał, and since we already know how to properly design a multimodule project, we can dive into details with how to wire it up with Dagger2. So I already assume you have some knowledge about Dagger, so we'll skip most of the basics, but if anything is hard to follow or not understandable, do not be afraid to ask questions. And that's it. Okay, let's start with some terminology. This is pretty fundamental stuff, but it can get lost during the discussion, so let's clear the air and be on the same page. First of all, constructor injection. If you use dependencies as constructor parameters, you are using constructor injection. There's no need to use any DI framework. Simply passing the right implementation during object construction is considered as a constructor injection pattern. That @inject annotation that you see here next to a constructor is just a Dagger feature, and it's not mandatory. Second of all, we have members injection. Members injection is when you provide your dependencies during runtime after the object is created. These are the fields annotated @inject, and they should be used exclusively for Android classes, where there's no way of overriding constructors. So activities, fragments, services, and broadcast receivers are the only places where members injection could be used. And since both Android and Dagger use a word module, and I want to talk about both, we will need to somehow differentiate them. In my talk, I will use the term module when describing Dagger modules, the ones that you put inside your Dagger components. And I will refer to library modules, so the ones that you specify on your build system level, like Gradle, as library modules, just like the documentation suggests. I hope that's clear. Okay, to understand where all this talk comes from, I will need to introduce you to HERMES. HERMES is a newspaper platform developed here in Schibsted. But the important thing is that it is a single project that builds into a bunch of different apps. We're not using any flavors. These are completely different apps. They share about 95% of their code base. And although it's not only the colors that distinguishes them, they have different functionalities called different endpoints. Some have different navigation, unique screens, different designs for navigation drawer, stuff like that. And that, of course, itself brings some challenges. But setting up dependency injection framework in that case is especially not easy. 2 years ago, when we started building HERMES, this is how we envisioned the project structure. The plan was to contain all domain and network logic inside a Java module called core. All the screens and presentation would go to UI, which was an Android module, and the configuration into a bunch of different thin, unique app modules. That didn't really work as planned, and the graph became a lot more complicated. Every feature we introduced was isolated into its own Gradle module. And once it was fundamental for the app, we exposed it as an external repository. That mindset forced us to think about all our library modules like separate artifacts, because we never know when they will be extracted from the project. With that in mind, we decided to implement dependency injection framework only at the top level of our modules graph structures. Because we assume that we cannot modify contents of the lower level library modules, because like if they were actually separate artifacts. Of course, this is pretty simplified, because core can be your hexagonal architecture, okay? You can have multiple layers here, you can have network persistence, they can be separated modules. But what is important here is that we have two base layers. One is a pure Java layer, and the other one is Android layer. But for the simplification, we will just use 2 modules for that. Okay, now that you know how we approach the subject, we can continue with features of Dagger that we use to achieve that proper architecture. Let us start with multi-bindings. Multi-bindings refer to a collection, so it's either a map or a set, of dependencies that can be injected anywhere inside our app. If we have multiple implementations of the same interface, and do not want to inject them all separately, we can use this feature and inject them all at once. Okay, so we have an example here. First, we have an app component, and it installs two modules, init module and an app module. This is our top-level component of one of the apps, just by the way. Init module is a shared module that provides us with two initializers. They both go into a single set. They cannot be injected individually because they both return an instance of the same interface. If we remove that into set annotation that you can see here, the code wouldn't even compile because we would have two providers for the same interface, so that's obviously illegal. App component also installs another module and its own app module. It is a unique module for that app, and it comes with one provider for some custom initializer. That's something that differentiates this app from the rest of them. And since it's in the same component, the initializer will become part of the same set. So we can now inject this set of initializers directly into the app or anywhere else in the dependency graph. In Kotlin, that @JVM suppress wildcard annotation is currently required, but the good news is that the guys from Dagger already work on fixing that inconvenience, so it should be ready pretty soon. Besides multi-bindings into sets, we can also multi-bind into maps. That works very similarly to sets, but it's also required not to specify only keys, but also not only values, but also keys. By default, we can use @string key annotation here, but if you're all up for some configuration, then you can write some custom map keys with whatever types you like. And this example is pretty similar to the previous one, but here we can see that objects are injected with a map collection. Another useful feature that can be used during designing your multi-module application are optional dependencies. What it means is that we can depend on object that we are uncertain will be present in our graph. They are really useful with different build flavors, multiple apps from the same project, so-called white label apps, or just if you want to have some debug dependencies that are not present in your release build. Let's look into one of the scenarios here. We have two components, one for a production build and the other one for debug. They both use view bindings module, which provides us with some dependencies, including an optional view overlay instance. The activity here is present in the main package, not in any specific flavor one. But in the debug variant, the component provides a debug view overlay, while production one doesn't even declare it anywhere in the graph. We can then inject an optional of that view overlay, and when it is present, then we can install it into the activity. The only requirement is that declaration with binds optional off that warns Dagger it is possible that the dependency won't be present in the graph anywhere. One problem with optional dependencies feature is that the class itself can either come from Java 8, so your minimum SDK needs to be 23, or from Guava library. So you can either hack your way around it or just add it into your project. That's what we did, unfortunately. Okay, so, but optional dependencies are they can get pretty complex, and this example will be more complicated, because what we will be doing here is using this optional functionality to customize the implementation of our dependencies. So we have an API interface and a repository that takes an API instance. That's like a simple case. There's also an API module that provides an API implementation and a bunch of other stuff that is not important right now. So let's say we have 4 apps. UI module and API module are in the shared library module that all of them have access to. Let's call it UI like in previous examples. That UI module includes an API module and uses it to create an instance of a repository that is being injected in multiple places in our project. But when the 5th app shows up and it uses a different NPI, we can do a simple alteration to allow the customization of that repository. First step is a custom qualifier. Let's call it custom API. UI module can then expect an optional custom API instance. as an optional binding annotated with our newly created custom qualifier. In the repository provider, we can now inject both a regular API and optional custom one. Then, if the latter is present, we can instantiate the repository using that custom API, otherwise proceed as usual. So if you want to use the unique API in one of your apps, you will simply need to install a module that provides you with a unique instance. In this case, I called it unique module that provides you with a custom API here. The good news is that custom qualifier does not interfere in any way with your existing providers. You can inject your regular API anywhere in your graph, but to get a custom one, you will need to explicitly ask for it, like in this example. And one little optimization here is not to use API directly, but to inject a provider of that API so that the object itself is not created and it's not needed. So using that, this way we can, our top level library modules can actually alter the behavior of the graph creation by providing that optional dependencies that will be expected on the lower level library modules. Okay, so I know that it looks a little hacky, but actually it works wonders in our setup, so I wanted to share it with you. Okay, now let's move into something more complicated, and that is components, but more specifically, subcomponents. Subcomponents are one of the best ways to encapsulate the hierarchy between multiple layers of the app. They are widely used in Dagger Android library to generate injection mechanism for Android components like activities and fragments. Subcomponents can be added to the graph in two ways. First, by directly adding into the component graph with a provision method in the component interface. Dagger will then generate a provider with a builder for that specific subcomponent that we can use. And the second way is by adding it into one of its parents modules in a subcomponent list, as seen in the second example. Let's look into our apps graph once again. If we decide to implement it as we envisioned in the start, it's very easy to design dependency graph using that subcomponents. In UI or in core just below your apps modules, we can define a subcomponent that gathers all domain objects and providers for all of them. But since a subcomponent has access to every provider of its parent, we can depend on interfaces which implementations will be then provided by the top level of our library module graph. So basically, Dagger can be used to configure stuff that is created in the library modules below. Here we can see a simple example. Child subcomponent configures its dependency using a configuration interface, but the actual instance is provided by the parent component. There's more to subcomponents, but we'll get there just in a moment. Let's go back to multi-bindings for a moment to visualize the hierarchy between components and their children. Like we all know that subcomponents have access to all their parents' properties. So we can simply provide dependencies to collections of their parents. Looking at the example, we have a single component with a single child subcomponent. Parent component provides a set of two initializers, while child provides another initializer that will go into the same set. But as you can see, both child subcomponent is injectable into child activity and parent component is injectable into parent activity. I named them just so that it can be easier to understand. And once subcomponent is injected, the collection will contain three elements: initializer A, B, and that child initializer added in the subcomponent. However, if we inject the parent component only, we will get initializer A and initializer B, because it has completely no access to the subcomponent that is being in that component. So it's kind of like inheritance, where subcomponents are like derived classes. You have access to what your parent has, but the parent doesn't know about its children. If that sounds good, I don't know. Okay, so another way of managing components hierarchy is by component dependencies. So when declaring a component, we can add another one or even multiple ones if we need as dependencies. That mechanism works a little bit different than subcomponents because these dependencies, they do not share bindings that are not explicitly exposed with provision methods. Just to remind you, a provision method has no parameters and it returns a type of object that is bound within the component, one that has a provider. Okay, so let's look at an example here. First of all, we have an app component that is declared dependent on the network component. Like we can see the declaration there. When creating this app component, we will also need to build all its component dependencies during the graph creation. But once we do, the API dependency that is included in that component can be injected wherever we like inside the graph. However, we will not have access to anything else that is provided within that network module, like in this example, OKHTTP client, which is used to create that API instance. So, as you can see, component dependencies are great for encapsulation, because if we do not want to expose all our dependencies everywhere, we can create a component that provides only a fraction of them, while it uses the rest of these dependencies to create other objects. Here's an example graph on how you can manage your dependencies in a multi-module setup. Just like in the previous example, core is where we have all the functionality and business and domain and business logic, repository, storage, etc. They can have like derived modules, hexagonal architecture, whatever you like. And UI is an Android module with all the screens, so activities, fragments, possibly presenters or view models. And it's also a home for UI subcomponent. And that UI subcomponent can be injected into all our screens and all our UI classes that we need. It depends on some objects that will be provided from its parent, like in the previous example, through some interfaces. And then, UI subcomponent can also depend on other components for encapsulation, as described earlier, so you do not need to expose some of your dependencies everywhere in your graph. And that app Android module is basically a tiny wrapper that only holds configuration objects and builds the app component alongside all its subcomponents that it needs. And this way we can actually configure stuff that is in our library modules below, and we do not need to use any flavors for that, because we have different modules for these specific applications. Obviously, this can be expanded further if the case requires. If your architecture is more complicated, then these modules probably will be more expanded, but well, that's just an example. And in addition to all of that, I also wanted to talk a little bit about producers. Because producers are an experimental feature, so it's not in the main documentation, and it's available from a separate artifact called Dagger producers. I will immediately warn you, though, that you will need to live with Guava if you want to use, if you're interested in its features. So the whole point of that extension is that it allows us to delegate object creation to a separate thread and access it only after when they are fully instantiated. If we have a bunch of really heavy dependencies that can take up to hundreds of milliseconds to initialize, we can asynchronously build them and benefit from faster startup. Producers introduce a couple of new annotations: a producer module, production component, and produces. As you probably guessed already, they replace in order module, component, and provides annotations. And while we cannot simply add produces annotated methods to existing components, we can add production component dependencies to the components that we already have. But before we set anything up, we need to specify which thread executor will be used to create our dependencies. To do that, we need to declare it somewhere in the graph with production annotation. In a producer module, we can then add a bunch of produces annotated methods that will return objects we need. They won't be created on the main thread, though, but on a thread specified by the declared executor. Produces method can be chained however we like, and Dagger will create the graph of thread, collecting and initializing all necessary dependencies first. These dependencies cannot be injected directly though. The generated code will provide you with a listenable feature of the type that you specified. So here we produced a bunch of initializers and bound them into a set. They can take up to like 2 and 3 seconds to initialize. And that initializer component can now provide us with a listenable feature of the set of initializers. That particular listenable feature that we get is an interface from Guava, which extends Java future. And using the futures API, also from Guava, we can add a callback to retrieve the object once it's ready. Just like that. Yeah, it's not simple, but here it is. Of course, we can use Kotlin and its extension methods magic to simplify accessing that listenable feature, but that will need to be written by hand though, since Guava is not really Kotlin friendly. And basically, that would be it. Dagger may be intimidating at times, but the sheer number of features and flexibility it provides can be really helpful in organizing our projects. But as with all tools, there are alternatives, and we should choose them depending on our needs. So I hope we have